Hello
So,
guys. Go.
so I'm Francis.
And I'm Elijah.
We're doing a presentation on trees. So, definition of a tree is that a tree is a nonlinear hierarchical data structure made of nodes. It starts with a root, and then every node after that is a child of the root, and there can be more than one or more child nodes. So, the parts of a tree are the vertex, which is the node, and each node holds a data. And then there's also the edge, it's what connects the vertices or the nodes. Then there's the root, which is basically the vertex that has no parent. And there are the leaves, which are vertices that have no children. Ancestors, which are parents, vertices that have a path to the vertices one layer below. And then there's the descendants or the children. And siblings, which are vertices that are on the same layer. And then a subtree, which are the trees that are composed of vertex and its descendants. And then within a tree, there are depths and heights. And then the depth is the number of layers starting from the root descending down to the leaf. And the height is the number of layers starting at the lowest leaf ascending up to the root. So there are some of the algorithms that comes with trees are the traversals. There are two main ones, the depth first traversal and the breadth first traversal. The depth first traversal starts at a parent node and explores each child before moving to the next sibling. And there are three kinds of depth first traversal. There's in-order traversal, pre-order traversal, and post-order traversal. In-order traversal is when you're traversing the left subtree, then visit the root, then traverse the right subtree. Pre-order traversal is when you visit the root first, then you go to the left subtree, then the right subtree. And post-order traversal is when you traverse the left subtree, then the right subtree, then you go to the root last. And then the breadth first traversal is when you're visiting each child of the parent node before visiting the rest of the descendants. And then other algorithms are searching, inserting, deleting. And most of the implementations of trees algorithm is recursion, so just keep that in mind. There are many types of trees. There are n-ary tree, skewed tree, expression tree, binary trees, and under that there's like binary search trees and AVL trees. Binary tree, we're gonna focus on binary tree, AVL, and BS binary search trees. So a binary tree is a tree where no node can have more than two children, and a binary tree consists of a root and only one or two subtrees. So the complexity of a binary tree is O to the n. There are no ordering rules between the nodes, and they can be a complete, full, or skewed binary tree. So their uses are for general hierarchical data representations, expression trees, or heaps. Then there's the binary search tree, which is a type of binary tree where the left child is always less than the right child. Well, the left child is less than the parent, and the parent is less than the right child. So the average complexity of a binary search tree is O log of n, and the worst case is O of n. So binary search trees enables efficient searching, insertion, deletion, provided that the data is sorted. And their uses are for searching dictionaries and like sets, etc.
And then we move on to the AVL trees, which is the Adelson, Velsky, and Landis tree. This tree is a self-balancing tree that ensures that the left and the right subtree have a difference in height of either plus or minus 1. So, in other words, if the left subtree is too heavy, then it'll rebalance so that the balance factor is either plus or minus 1. The balance factor has a simple equation of the height of the left subtree minus the height of the right subtree. The complexity of this is O of log of n. for rotations, a simple rotation would be if it was too left heavy. So then this has a balance factor of 2, in which we would take this node here and perform a right-right rotation, in which this would be 2, 1, and 3. So that is a left-left rotation.
Right.
Sorry, it's right-right rotation. And then vice versa, if it were the other way, you would take a left-left rotation, and if it were something like this, then you would take a left,
You take a right
Right,
rotation,
left.
then a left.
and then a left rotation to balance out. The complexity of this tree would be O log of n, and the uses for it would be databases, memory indexing, scenarios requiring fast lookups. And then at the bottom there we have a bunch of different rotations to balance it out. And then after that we have expression trees, which are basically a tree in which every non-leaf node represents an operation between 2 children and a leaf node that represents a value, a variable to be operated on. So a quick expression tree would be, in the example as follows, we could just say plus, plus, times, and these are all non-leaf nodes, so they are operators, and then the leaves would be your operands. So based on the expression tree in the handout, if we were to do a pre-order, what it would do is it would go from the node to the left subtree all the way down, and then the right subtree, and then all the way to the right subtree. For in order, it would take it kind of like a binary search tree in which it would take the leftmost child, then the node, and then the rightmost child. For post order, it would take all the children in the left subtree, and then all the children in the right subtree, and then go back up and take the parent nodes. There are only 3 parts to the expression tree, which are the leaf nodes, which are operands, internal nodes, which are operators, and then the root node, which is the final operator. Complexity of the expression tree would be O of n, where n is the number of elements in the expression. And these are good for a lot of compilers for language and calculators. And then we have why are trees important on one of your last information pages. So trees are great for storing data that naturally forms hierarchy. For example, most file systems in computers, they are structured as trees, so you have folders and subfolders, and each side subfolders you have more folders, and then they enable efficient search, sorting, and hierarchical modeling, which make them essential in areas such as databases, compilers, and even networking. Trees underpin routing tables, they multicast structures, and they also have shortest path algorithms. They also bridge the gap between linear structures and complex graphs. And then onto our exercises, we just have 4 pretty basic problems for you guys to solve on trees. Yeah, that's pretty much all we have.
Are you guys going to be writing stuff?
Really?
Okay. I think it was noted that I didn't have a turn-in location, so if you want to email all of your materials, email it to Finn and copy me. That work? No way, she has everything too.
Okay.
Alright.
Alright, well, perfect. So we're going to be going over stacks and queues. So we'll start with stacks real quick. Basically, what the definition of a stack is, it's a list with the restriction that insertions and deletions can be performed at only the end of the list called the top. So if you see the first picture, right, the 2 is the only one that we have access to. That's the last element that we pushed onto the stack. An insertion is inserting something on the top of the stack. Deletion, pop is returning that element and then removing it from the top of the stack. And then p/top, it says top in the book, it returns the element at the top of the stack without removing it. So one way that I was thinking about it is it's kind of like a stack of books. It's like you can't take off the bottom book without it falling apart. So you can only take the top one off every time until you get back to the bottom. And then one reason why it's important is just because it's a type of list and it's supported by both std list and vector. It's a constant time operation. Another neat tool about stacks is that it actually reverses the order of items, right? Just like the books, it's like you put, like since you're putting at the top every time, you're reversing whatever you put in, right? Whatever you take out is the reverse. A couple of popular implementations are a linked list, right? So you use a stack as a singly linked list, and then every element that you push is going to be a new head, and then when you pop that element, it's going to return that head, and it's going to shift it by 1, which removes that old head from the linked list. Another popular implementation is using it as an array, which works with std vector. And basically it uses the index top of stack, and the way to push it is by incrementing top of stack, and then you set whatever the array at index top of stack equal to x, and then popping it is returning that array at index top of stack, and then decrementing it, so you go top of stack minus minus. And one thing that I noticed while I was reading about this is that we're not actually erasing anything from the array, unlike the linked list. Instead, we're just moving the index top of stack, and I kind of thought about it as like a spotlight. It's like you're only having the spotlight at one thing, and you just move that spotlight over and over. And basically, what makes stacks really good is just the fact that their time complexity is constant because we're only looking at one thing every time. We're not traversing through the whole linked list or the array or the whole stack. Every single time it's only one. And then a real life example. So I grabbed this quote from the textbook. I thought this was pretty cool. It says the fact that most modern machines have stack operations as part of the instruction set enforces the idea that the stack is probably the most fundamental data structure in computer science after the array. And then one example that I thought of is like web browsers and back buttons, right? So like the browser with URLs is stored on the stack, and then it's like every time you press the back button, you're popping it from the stack and you're going to the last one and looking at the stack. Yeah, and then now we can move on to queues.
All right, so for queues are another type of list where data is added to the rear and then it's going to be taken off from the front. So this is going to be the first in, first out, or FIFO type of list. So an easy way to think about this is like a waiting line or like a Starbucks line, right? You go to the back of the line, the first person in line, they're the first one in the order, and then it just goes down the line as it goes. So those operations are going to be called NQ, so that's where you add to the rear. And then DQ is where you take off from the front, and then you can also have the operation of current size just to let you know what the size of your queue is. For NQ and DQ, it's going to be a big O notation of 1 because they're just simple operations, but if you want to search through a queue, it's going to be big O notation of N, so it's not the most efficient for searching through a list of data. And so you can implement these yourself by making a linked list or an array, or you can already utilize the queue class that's already implemented into C++. So why is this important? Again, like Max was saying, these are fundamental abstract data types within C++. There's many real-world use cases that I'll go over on the next slide. A lot of real-time systems, so again, I'll talk about them more on the next slide, but they all use queues. And then as we learned earlier in our current lab, you can use them to work with graphs too when you get into more advanced types of queues. So some real-world examples I thought of was like printer queues. So if you want to print a bunch of documents, the printer is going to put that in a queue. So the first document you tell it to print, that's the one it's going to print first, and then it's going to go based on the order you told it to print. Support ticket system, so if you're having trouble and you have to send a ticket to the IT department, they're going to solve issues based on the order that it came into them. And then event handling system, so like every time you click on a mouse or you do a keystroke, the computer's going to process that based on the order that you input it into the computer. And so there's another good graphic where you can see NQ is at the end or the rear, and then DQ is at the front, and then there it's numbered, so it's a good visual for how each data was input into the queue. And yeah, that's all I have for queues. So.
Great. Thank you. Who's up next?
It's charging, yeah. It's displaying it.
Would it make more sense? Does everyone want a copy of this information?
This is big to get now.
Oh, yeah, yeah. You guys send the email to Finn, copy me, I'll post it.
All right, so we have hashing. Luke,
I'm Blake.
so a hash table is a data structure that has an array of a fixed size containing items, and those can be like, your name and maybe your ID number based on like the place you work at. So items can have things like strings to hold the name and integers to hold maybe your ID number or your age or anything like that. It's placed within the hash table from 0 all the way to table size minus 1 until there's no room for any more items in the indexes. And then you're going to use a hash function to distribute the keys among the table, because most likely you're going to have more keys than you are amount of spaces inside your hash table. And then, so your hash function. So typically you use key mod table size for just integers, unless it has a sort of pattern, because then a lot of keys are going to be put at the same index within the hash table. So typically you use a prime table size, not a size like 10, but something like 37 is the most often used one. And then a simple string-based hash function are often used, but distributed poorly because a lot of words can start with the same letter, so it put them at the same spot within the hash table and just kind of mess up the method of evenly distributing it throughout the hash table. And then if two keys hash in the same slot, a collision occurs requiring a collision resolution method, such as separate chaining or open addressing. And so the way separate chaining works is it handles collision by storing all the elements within the same hash value in a linked list, which is like a bucket. Right? So every hash section has their own linked list. And searching and inserting involves hashing to the correct list and then traversing. So search for that index and then go through that individual linked list to look to search what you're looking for. And then hash table classes store an array of linked lists and require keys to support hashing inequality. And then custom types like an employee class, like if you were, you had your name and your ID number, maybe your parking space or something like that, can be stored using the equal operators and a hash functor. And typically they're implemented with a polynomial hash, such as a 37 base method. Like I said, it's a small prime number and it helps spread out everything evenly so that there's not a lot of collisions within the hash function. And then the load factor is the number of elements divided by the table size. And this determines an average list length. And with good hashing, lists stay short, making separate chaining efficient without needing more complex structures. Probing hash tables avoid linked lists by trying alternative table positions using a collision function, but they require large tables and generally keep a load factor below 0.5. Linear probing uses function I equals I, checking cells sequentially. It's simple, but because it's checking them one by one, it's super slow and yeah, it causes probe sequences and poor performance as the table fills. So as you put in more functions into the table, that just means it has to check even more functions until it finds an empty spot. And then the inspected pros for linear probe rise dramatically as the load factor increases, making it inefficient when a table is more than half full. And then clustering makes performance significantly worse than ideal random probing. Quadratic probing reduces primary clustering, but can still fail to find empty slots because it only looks at about half the table. And if the table exceeds half capacity or the table isn't prime, again, it's only exploring half the table. And then rehashing is triggered when a hash table becomes too full or when the quadratic probing insertions fail. A new table about twice the size, usually the next prime numbers, that when you're searching, it doesn't mess up. If it's still using a size that ends by 0, any index number that ends in 0 will give you the same index. And then once it creates that new size, it just puts all the old hash functions inside the new hash function. That has more space. It's expensive. It's a big notation of n, but it happens rarely. Typically when there's a lot of insertions in your hash function. So the average cost per insertion remains pretty low. Rehashing strategies vary. Typically you hash when it's about half full, when an insertion fails, or when it shows a load factor is exceeded, with the last option given the best performance. And separate chaining tables also support rehashing, creating a larger table and reinserting all the elements from the old list into the new positions.
And C++ 11, which is the one we've been working on in this class, actually has a hash table in the standard library. So we have the map and the set, but the hash version of these are the unordered set and unordered map. So the items stored in the ordered set must provide an overload operator. So an overload operator, so you have to overload the equals so that way you can determine if the items are equal or not. And then similar to the set and map templates, they can also be instantiated with a function object that provides an override by default. And the unordered set and ordered map can be instantiated with function objects that provide a hash function and equality operators. So there's one that's in C++ 11. They have the hash function and the equality operator by default, but you can override those if you want to make your own classes and objects that be stored here. Okay, so kind of the goal of the whole hash table in general is to have access to your data with O of 1, so constant. That's kind of the idea of the hash table. So we want to try to make it so the worst case is O of 1. And so there's different ways of doing that. So there's an example here. So assume that in is known in advance, so there's no rehashing needed. So if we know the number of items we're going to store in the table, you wouldn't need to rehash, because obviously you can make your table appropriate sized. So you're going to automatically get that worst case of O of 1. And then if you don't know the size in advance, there's something called perfect hashing. And so the issues we might run into is there might be too many collisions, which we would lose that O of 1 access. So there's a couple ways to address this. One would be making the table very, very large, so you wouldn't have that problem. But then you run into the problem of it being unnecessarily too big and wasting memory, because in C++ that's what we're trying to do is manage memory. And then another problem is you might just get unlucky. Like, we know how statistics work. Like, even if you have a super large table, you can still hash something and you can hit that same index over and over, and you might lose that worst case. You might run into the worst case where you break the O of 1. So perfect hashing is a solution for this. And then we have something called universal hashing. So this has two things that require it to work. So the first one is the hash function must be computable in constant time, and the hash function must distribute its items uniformly among the array slots. So universal hashing is like when let's say you run a hash function and you're getting collisions. Instead of chaining them, you can run a different hash function. And that's where universal hashing comes in, where you have a list of different hash functions and you run one randomly based on if there's collisions. Does that make sense? Do you guys understand what I'm saying? So you run a hash function, you get collisions, and you're like, oh, we don't want collisions, so you run a different hash function and see if that doesn't create those collisions. And you can keep, so that way you're maintaining that constant. So we have our real world example. So the real world example is a library book catalog. So you go to the library, I don't know how many of you guys have been to a library recently, or, and you have the ISBN number. That's that ID that identifies every single book. And so where we could do this is you would hash that ISBN number and get an index, and then store the books in that index. So if you need to look up a book, you would run the same. So like let's say you come to me and say, hey, I need to find this book. I run the known hash function on that ISBN number, and I get that index, and I can instantly know where it is. I don't have to search the whole library. I instantly know where it's going to be because it's out of that index. And so at the bottom where we say storing, you run the hash function, you get the index, you put it there, retrieving. You come back, say I need this book, I run that again, same hash function, I know where the index is, and I grab it. And then why hashing is important is what we talked about, is it makes it efficient to be able to search a large amount of data in a constant number of times, so you don't have, it's just an efficient way to store and retrieve data.
Thank you.
Is it on?
It took a second for it to load.
So, it doesn't have to be plugged in for live. It doesn't matter. Yeah, so we go, that is a screen share.
Oh, okay.
And then make sure you're connected to this classroom. As soon as you do, get this to fire. You have to also come back here. So,
Okay. We're doing sorting algorithms. I'm Ian Serena.
Hi, Serena.
Okay, so what are the sorting algorithms? So we generally have like a list of variables, and we want to be able to sort these guys. So we're going to want to sort them from greatest to smallest, or smallest to greatest, and it could be anything. So it could be names. We do any sorting thing, but we want to be able to have it so that it's sorted and it's our ordered list. We usually do this via like inversions. Inversions is just like a way to just switch elements inside of the list so that it could become ordered. Usually these sorts are measured by their efficiency, so we want to know these efficiencies to know which one would be best in our use case scenario. Like all of them have different efficiencies, so we make sure that we note those. It is important because it allows us to manipulate our data so that it's sorted, ordered, and easy to use.
Okay, so this is a bubble sort. It's like one of the simplest sorting algorithms because there's a bunch of different ones. So in the bubble sort, it goes through your vector or your list of numbers or variables or whatever you have, and it just compares the two. It compares the first and the second, and then if there needs to be a swap, it'll swap it, and then it'll keep going all the way until the end, and then it'll keep going until the whole list is sorted. So as you can see in the visual, this is what it does. It does the first pass, and it swaps the first two, and then it swaps the second two, and then it swaps the last two, and it keeps going through. Okay, so it has a O of n squared efficiency as the worst case scenario. So, and this is because you're looping through the list amount of times in the worst case scenario. So that the worst case would be if it was backwards. Yeah, and then we came up with a little memorize by for each of the sorting methods because there's a lot, and so it's kind of difficult to remember how to go about doing each one, how to go about understanding each one. So this one is kind of like, because it's really slow and like it's very simple, you just kind of have to like switch and pray that it'll be fast, switch and pray that it's not the worst case scenario, so we call it the switch and pray method. Yeah.
So the next is selection sort. This one is like, it's the same efficiency as bubble sort. So that is going to be O(n)(2). This one, instead of bubble sort where you just keep on switching them, you're going to prioritize the least. So you're gonna find the smallest one. So you're gonna search through the list. You're gonna go see which one is the least compared to the. So for the example, the starting point is 5. You're gonna find the least out of the rest of the list. If you find the least, you're gonna swap them. You're just gonna keep on doing that. You go to the next. What's the least? 4. You're not gonna swap 2. You go to 3. What's the least? You're not gonna swap them. So you just go through the list and you keep on swapping anything that's smaller than what it is. So the reason why this is O(n)(2) because you could start at if you start from a decreasing list, you're gonna have to start at 9, go all the way through the list to 1, swap it, and just keep on doing the list. So you're gonna go sort through the list n amount of times. And we said we could memorize this by prioritize the smallest first, because you're just gonna keep on finding the smallest, just put it in the front. So that's selection sort.
Okay, insertion sort is kind of similar to selection sort, but like backwards a little bit. So it does it by going through and prioritizing the largest. So it creates kind of like a new list from the unsorted list, and you take the front from the unsorted list, you add it to the new list, and then you keep repeating the process and adding to the sorted list and putting it in the right position until the unsorted list is empty. So like in here, we start with 23, and then we have our new list on the right. And so it goes, 1 is less than 23, so we put it in the new list in front of 23. And then we keep going, and we have 10, which is in between 1 and 23, and it does a least comparison, and it goes in between. And then we have 5, which is greater than 1, but less than 10, so it goes in between. And so it goes through all the way. And again, the efficiency is O(n)² since it can loop through the list the size of the list amount of times, which, like, if in the worst case. And so we call it memorize by prioritizing the largest first because it's very similar to selection sort, except it's the largest, not the smallest.
Cell sort. Cell sort is a tricky one to understand, but essentially it's a version of insertion sort, but it uses a gapping sequencing to find the shortest path. So this isn't the completed gap sorting algorithm, but essentially, so you're gonna have like a sequence of numbers, and you're gonna split up the list into the sequence of numbers. Like, so for example here, there's a sequence of number like 17, 44, 54. Here's a sequence of 26, 55, 77. These sequences are already like determined inside of there, inside of the algorithm. So it's just gonna go find these sequences, it's gonna order those out first, and then it's gonna use those sequences to sort a more efficient graph. So it's kind of the same as insertion sort, but with these added graphs, how speed up the process. This has efficiency of n log n, as n log n is generally the fastest you can sort these graphs, as you're still going to need to go through the graph like n log n amount of times. You can't be n. So that's shell sort.
Okay, heap sort. This is another really complicated one, and we didn't really talk about it a ton in class, but we've worked with it a little bit in our sorting lab and kind of in our current lab. But so it's using a binary heap structure to sort an array of values by placing the smallest or largest element and putting it at the front or the back of the list. So it's kind of complicated, but what it does is you have your heap data structure that's already built, and then you kind of sort based on your heap data structure. So it there's the heapify. So you swap the root with the last element, and then you heapify the root, and you keep repeating until it's sorted. So it's really complicated in this graph or this visual, but as you can see, the efficiency is n log n, which is the fastest kind of algorithm. I know you're just talking about that. So it's generally pretty quick and generally pretty useful in things like the current graph, lab assignment that we're using right now, where we're talking about min heaps and binary heap structures. So we can memorize this one based on binary tree, because this one kind of utilizes trees in the sorting, so that's how I remember.
This image wasn't really the best because
Yeah.
essentially I thought it was good because this is the only one with the heap, and I thought this is a great way to show it. But essentially the sorting is from here to here, and then this whole thing is just there.
I know that at different times I've had different amounts of people in class, but were you guys here when I did the duffel bag analogy?
Yes.
Okay.
Well, maybe.
Yeah.
I don't know if I was.
It wasn't the most memorable.
Is that the passport? You need the passport.
Yeah, you have the passport at the top of your bag.
Yes.
So,
He told us about that.
all right.
It's like that. There's the heap data
Yeah.
structure.
It's kind of loosely organized below, but you know that the important things at the top.
Yeah.
All right.
So, but yeah, this one's good because it actually shows you what the tree looks like, and
Yeah.
it's interesting because it uses the tree.
Okay, quicksort. I like quicksort. So essentially, what quicksort does is you're gonna have a pivot. So for this one already starts with a pivot, but you could choose a pivot from anywhere for the first one. So you're gonna create a pivot. So this graph goes in the middle. So the pivot's at 5. Then you're gonna have 2 subgraphs from that pivot, the left and the right. You're gonna arrange it around the pivot. So anything less than the pivot is gonna go to the left of the pivot. Anything greater than the pivot is gonna go to the right of the pivot. It's not ordered yet, but it keeps on doing this. So then you're gonna take the farthest value right, so 6 and 2, and you're gonna have that as a new pivot. So then you're gonna do it to the subgraph. Anything to the left of the pivot is smaller, anything to the right of the pivot is greater. You take the right of the new subgraph, that's the new pivot. Take the right of the subgraph, that's the next pivot. And essentially when you keep on doing this, you're gonna have an ordered graph, because you're gonna have everything to the left of the pivot be smaller, everything to the right of the pivot be smaller, and you're gonna have other pivots that have the same thing going on. And that's essentially what quicksort does. Quicksort also has efficiency of O(n) log n. It's the fastest, and they're all the fastest. Quicksort generally is faster though, due to other efficiencies that it could. I forgot what it was, but even though all 3 of these have the same O.
Worst case.
Yeah, the worst. Well, these are the best case. Because I'm
Worst case is the same.
Big O measures worse.
big over. Okay. Sorry.
But the non-worst case for quicksort is better, basically.
Yeah, it's generally more efficient, and I memorize this by pivoting. So that's generally good.
And then also your pivot can be anything. It can be, in this image, your last, you made the last value is the pivot. As you can see, 2 of the pivot, and 6 becomes a pivot. But it could be the first value, or it could be the middle value. It doesn't necessarily matter. You can make it whatever you want, whatever's best for your data set. But yeah, I personally like this one. I think it's really easy to visualize with the last. Yeah.
So this one starts in the middle, and then after that it goes to the right.
I think so.
I think it doesn't show the first
Yeah, it doesn't
unsorted
show
thing.
the
So I'm pretty sure this is only getting the pivot from the end.
Yeah, I think
So
the
I'm
first
pretty
one
sure
sort of falls.
5 used to be the end of the list.
But it doesn't show it, but I think so. Because the rest of them are at the end. Oh, okay, so merge sort is a recursive search. So basically, I like to think of it, okay, it has nothing to do with trees, but it reminds me of a depth first search. But a recursive, like it does it via a recursive search that will continually split up the list and compare those arrangements until it's ordered. So the green numbers represent the order in which the steps are happening, and then these are like your list numbers. So if you start at 1, it splits it into 2, and then it compares here, and it compares each 2. So here's step 2, goes down here, and it compares. And essentially, once you get down to the like individually broken up compares, then it's gonna reorder it down here, and it's recursively. So like that's why you go down and then it like swaps. But this visual, I like it because it reminds me of a depth first search. It's not, but it reminds me of it because it's like going down and then recursively like swapping everything. And it also has a time complexity of n log n because it uses a recursive divide and conquer approach. Yeah, and so it's pretty efficient. And then I memorized this one based on split up recursively because you're using recursion in it. And yeah, and like when you do tree searches, use recursion as well.
I also like this graph. I just wanted to add, usually when you see a graph of this, it's usually just this top part, because this is what it does when it goes down. But this part down here is when it goes back up the recursion. So that's why I like this graph, why we chose it, because it's able to show what's happening. So your recursively divides everything up, and then once you have everything divided up, it's going to go back up. And make it sort of. This is our like memorization table. So this is just like the list of all efficiencies and like our little cache phrases for them. So for bubble sort, it's ON2, switch and pray. Basically, you're just switching them to get the. Hopefully you get the quickest ordered array, but it's generally gonna take a while. Selection sort, ON2, smallest first. You're just finding the smallest, putting it in front. Search and sort, you're finding the largest and you're putting it in front. All 3 of those are N2, N squared. Shell sort, O n log n is gap sorting. You're gonna find, you use these gaps. Gaps is basically what they call these sequences to sort the list. Heap sort, O n log n. It's just a binary tree. We use this in the lab. This is a great example of a real life situation where if we have a network and we want to find the cheapest things, we're gonna want to use a sorting algorithm to find it, the cheapest, so we don't have to do it manually. Quick sort, O n log n. We just set it by pivoting. That's kind of the best way to describe it. You're making a pivot and just switch everything to the left and the right, and you're just gonna keep on doing that. And then merge sort, O n log n. And then split recursively, so you're just gonna keep on splitting down that list until you get the ordered list.
Okay. My name is Noah. My partner Finn is not able to make it today, but I told her that she could do the visuals parts. And basically, since we're talking graphs, and graphs are what the lab is, I was going to give you guys some insights into the graph. Graph traversals. So, I want it to be interactive. I want to know who's at a sticking point. You know, you're just at a sticking point. Yeah. And then, yeah, there we go, nice and tall. And then if we could hear about it, because I guarantee you, nearly everybody's stuck somewhere. And we all struggle at different times in different ways. So let's hear, where are you at so far?
I guess like I understand location, I understand node, like I understand like how all that works, and I get how to go like from one location or node to the other, making node from the location, the cost, and grab everything. I guess for me, the thing that I'm stuck on is just the min heap, and that's like the priority queue.
The min heap.
Stuff like that.
I'm repeating for the video.
Yeah.
Okay.
So mainly just that. I haven't spent as long as I should have like tinkering with yet, but like I've been trying to make the min heap myself.
Oh, okay.
But I saw yours and then I'm like, okay, I should probably.
You could be inspired by it. You could just say, I could do better than that.
I don't think I can do better.
Well, by the way, you guys did a great job. I might just post videos next semester and make the class remote. No, the MIT videos are great. You watch those guys with the chalk and you're like, wow. Okay, so I'm hearing you. We're not even sure how to articulate where we're stuck.
I guess I'm stuck on like how to implement.
Okay. So is everybody, even though I provided it, is everyone wanting to do their own min heap? Okay.
I was working on it.
So I've provided.
I think it's just him.
No, so that's fine. So I provided it, but so some people are stuck with like, how do I use this? What am I doing with it, right? Okay. So I've got a few examples that we can work through. Let's see. I gave you guys, I think about doing announcements. I start to draft them, and then I might not end up sending them because I'm like, it's like a bullhorn. You kind of want to think about what you say before you announce it. So let's see. Three. We're gonna do a super basic map. S, mountain. So to start, the mountain, the goal, and we've just got grass. So I should have given you guys this as the demo starter graph. Because I think it's our tendency to look at computer science problems and immediately start thinking. And say, I know this. This is not that hard. How can I answer this?
Is this, should we have one more row on this one?
Oh, you're right.
Let's take a grass.
Yeah, I mean, or we do,
Or just
right. So I have a couple. So we're here. We're at the start node. This is the way that we think of this as a node in a graph, but really we know it's a grid. So, and each node itself has a cost, which means for us to travel from one to the other, we're going to need to incur the cost that's inherent in this. So that's where it goes a little bit outside of our concept of graphs into traversing this map. But the concepts remain, we just have to do some mental gymnastics to get there. So I'm at start. What we do is so that's what I have. I have a map that I'm reading in, and I know that I'm starting at S, right? Because that's what we have in our terrain map. So at S, 0, 0. We push that in the queue, then we go into that section where we're working through a queue. We pop it back out. We're considering 0, 0. We need to look around. I'm not sure. Oh well, I'm not going to move that around. We need to look around. I've seen several of you guys coding this by hand, which is great. And you do want to code it by hand, and you're going to start with initial ways of doing it. But we think of a different way of doing this. So blew me away. I have a friend who grew up coding C with his dad. And the way he approaches problems is different than the way I ever think about approaching problems. I think like, no, I want to look all around. Well, you just think of your direction of rows and your direction of columns, and maybe we could even call it an index to remind us that there's a direction of rows, index, direction of column, index. And then we're going to look at, because you remember the example I did, where if we were at, say, a position of 2, 3, and we want to look at this spot here, this one here, and this one here, we're going to need to consider our map structure, which the map structure, the reason we say rows and columns, and the reason that some people, including myself, will get mixed up and confused is because we always think X, Y.
Yep.
But it's not. Because we have, the data structure is such that the first data structure is holding the index of rows. So these are rows, but what we get is the index of the row. So 0 is the first index row. So when we have 2, are we at 0? No. We're at 1? No. We're at 2, so we're at this one. So 2 gives us how far down we are when we put it out in a space like this. And then 3 is going to be 0, 1, 2, 3. And so if we were here, we'd be considering at the time, so we'd erase to infinity, which is the initial value of everything, and we say we want to look at all the spaces around it. To do that, we have to do this math that we talked about, where we look at a -1 and a 1, a 0, and a 0. And these are paired up. And what we're doing here is we're looking at these sets. We're utilizing the same index to get these pairs. So in a loop, we can say for I equals 0, I is less than 4. It feels weird to hard code a value in there, but we know we're going to just do 4. I plus plus. And so this is how we look around. We're going to end up looking around there. We've hard-coded a loop that will always consider all the neighbors. And for each one, we already have is valid, right? So when we are at a starting point on this graph, starting point here, we say look at neighbors. And is valid is going to keep us from going here and here. So we check this, we check this. Shoot. I want to get you guys to the aha moment. So we're here, we consider this neighbor, and the cost of getting there is 15. The cost of getting here is 1. As a computer algorithm, we're never going to see the goal here, or the graphs, or anything else. We only consider it in those directions first. Next, what we're going to do is so when we look and see these are the neighbors, then we're done considering this. We gray it out. These two are in the cube. We pop one out of the cube. We first pop this in the cube, out of the cube, and we consider the neighbors here. We end up seeing this. At some point later, if this is a more complicated graph, or if I had done the weights differently, and we had something more interesting going on, we would end up popping this off the cube, because when we put this back in the cube, but at some point later we pop this one off the cube, and we see that this is next to the goal.
Wow.
And the cost of that is 15, and then plus 1 to get to here. The cost of getting to the goal is 16. So at that point, we would know that to get from start to the goal, we have a path in 16. And it's not until we've processed this one and where it can take us that we end up finding a better place, a better way to get to the goal from the start, which is 1, 2, 3, 4. And so then we would update our best way to get there to 4. So in order to do what we're used to doing, which is graph traversals, and we're used to keeping track of things in lookup tables, what we're going to want to do is step by step traverse our graph, keep track of the paths, and we're going to need to keep track of the best cost so far. So we have a value cost to get to any location, and the best cost so far, and the path that we've traveled. You guys keeping up with that?
Yep.
Okay.
Well, Dijkstra's keeps the cost in mind, but it doesn't necessarily take the cheapest route. Right?
It does. Dijkstra's is greedy with a bigger picture in mind. So
At least
it-
steps to get there versus cost.
So when I've traveled around, my wife's good at this. She'll be like, okay, how do you get from here to here? And she's like, okay, you could get off the plane and get on a subway and take the subway to here, but then you can get on a bus, and then from the bus you can get on, and you have to just add all those different costs of different trips. So Dijkstra is going to say, okay, taking one long train trip might be easy, it's simple, it's one trip. But if we cut it up into a bunch of little trips, maybe those little trips are more effective. So Dijkstra will keep track of all the trips together and each individual trip. Whereas a greedy algorithm only looks at what's the next trip I'm taking and which one's cheapest.
I thought that with Dijkstra's we would not even get to. I didn't think we would get here. I didn't think we would even get here to even look at this, because Dijkstra we would just take the shortest one and then we would just keep going from there.
Yeah, so if we come here and when we come here, then we would consider the neighbor. This will be back on the cube. But this is, I forgot to apologize to you guys that had I thought this out a lot more thoroughly about what makes it really compelling, I would have never put in the 250. the crazy different weights, everything would have been like 1, 1.5, 2, 3, something where it's like very easy where you get into places where it would be compelling to go either way.
Well, but
Next time.
when you program the algorithm doesn't care if it's close, right? It'll still